One of the incredibly useful ways to use linear regression models is as prediction models or predictive models. So if we're thinking about what is prediction, we're thinking about trying to make educated guesses as to the values of unseen observations. Typically, we're going to be thinking about trying to apply this into the future, so using data that we've collected in the past to make educated guesses about what we might observe in the future. Now, there's a sort of key distinction between estimation and prediction, and that's the idea that with estimation, we're trying to characterize a distribution, whereas with prediction, we're trying to actually get at the single value of something that we've not yet observed. And so there's sort of some fundamental differences, but regression models are really well situated to be used as prediction models. So if we think about a fitted linear regression model, this can be used for the purpose of prediction. If we think about point predictions as guesses for single values, we can also form prediction intervals in order to quantify the uncertainty that we might have with our predictions. So how can we think about prediction in light of linear regression? Well, in the linear regression model, we can be viewed as modeling the conditional mean, so the expected value of y given x is equal to x, and that's going to give us beta 0 plus beta 1 times x. So that's one way that we can view what our linear regression model is. However, we can also view it as characterizing the actual observations. And so if we've assumed that y is in truth equal to beta 0 plus beta 1 times x plus epsilon, right? Then this beta 0 plus beta 1 times x, right, this term that we have here, is in some sense trying to capture out the meaningful value for y. We know that y is not going to be exactly equal to this. We have this plus epsilon here, but this plus epsilon is sort of a random error term. So we're not going to be able to take a guess based on this. It's totally random, but this first component gives us a good guess as to the actual value of y. So we can view it as actually trying to model specific values as well. So our best guess for the value of the outcome, given a value of the predictor, is going to be beta 0 plus beta 1 times x, because we can't take a guess on the basis of that random error. If we frame it in this way, we may ask if we have a previously unobserved individual has some explanatory factor, right? So x is equal to little value of x. What is our prediction of the outcome for that, right? So we have never seen this data point before, but we want to know, well, what do we think the outcome is going to be based on an observation of the explanatory factor? And the idea is that we can make the best guess as being beta 0 plus beta 1 times x. Now, ultimately, we don't know beta 0 and beta 1 exactly, and so we'll have to estimate them. But if we use our estimated values, that gives us beta hat 0 and beta hat 1, and we can use those to actually form our concrete predictions. So we take y hat to be beta hat 0 plus beta hat 1 times x. And so that notation of using y hat here is sort of indicative of the fact that we're using this as a guess for the value of y. So we know the value of x, we want to guess what the value of y is actually going to be. Now, epsilon is purely random, and as such, we cannot predict it. There is nothing that we know in our observations that's going to help us predict this, and so we have to sort of ignore that fact. We know that our guess might be a little bit too high, a little bit too low because of that value for epsilon, but we can't sort of inform more about what epsilon is. However, we're still going to end up with a relatively good guess using beta hat 0 plus beta hat 1 times x. So this is framed as a problem of prediction. We want to guess the unknown value of previously unseen data. Whenever that's what we're trying to do, we're trying to predict. Again, this is substantively different than trying to estimate the value of a parameter from an unseen distribution, right? Instead, we're trying to guess specific values in our data or data that we have not yet observed. Okay. So if we think about this as being sort of separate from estimation, we might also want to quantify our uncertainty in prediction. Quantifying uncertainty in estimation is an important task of statistical inference. So what about quantifying uncertainty in prediction? So there is uncertainty that comes from a couple of different places, right? So we have uncertainty in our estimation of beta hat or of beta 0 and beta 1, giving us beta hat 0 and beta hat 1. And this is going to be captured by the sampling distribution of each of those estimators, right? So if we have the sampling distribution of beta hat 0, the sampling distribution of beta hat 1, there's going to be uncertainty there, right? So we sort of can capture that or write that down through those sampling distributions. But even if beta 0 and beta 1 were known exactly, there's still going to be uncertainty in our predictions. And so why is that? It's because of the random error term that we have, right? So y is going to be beta 0 plus beta 1 times x plus epsilon. That epsilon term, even if we knew exactly beta 0 and beta 1, we still wouldn't know epsilon. And so we're still not going to have a perfect estimation. We get that sort of extra variability here. So taking y hat to be beta 0 plus beta 1 gives the difference between our prediction and the truth as being equal to epsilon, right? And so we have our two sources of variability here, or of uncertainty here. There's the uncertainty that comes from estimation, and then there's the uncertainty that's inherent to the problem of prediction itself. So we can think about the total variability as being the sum of each of these sources of variability. Okay, and so we can take the variance from our prediction, we can take a variance from our estimation, we add those sources of variance together, and that's going to give us the total variability or the total uncertainty of prediction here. And so we get a total variance of sigma squared times 1 over n plus x minus x bar over n minus 1 times sx squared if we are looking at the variance of parameter estimation. And so this comes from looking at the sampling distributions of the parameters for beta 0 and beta 1, right? So beta 0 hat and beta 1 hat, we get a variance of the sum of those multiplied by x of this term here, okay? And so that's going to be sort of the first component there. We get variance of sigma squared from the random component, right? And so that's just the variance of epsilon itself. And so this is going to lead to a total prediction variability of sigma squared times by 1 over n times plus this component, right? That's this first piece here, plus sigma squared. And so if we sort of write this in a more condensed form, we get sigma squared times by 1 plus the term that we had from our variability before, right? So it's going to be sigma squared 1 plus this component here. And that's going to be our total uncertainty, our total variance, if we're looking at this as a prediction problem. So then we can think about, well, we have predictions and we have prediction intervals. Just like within estimates, we would have a point estimate and then an interval estimate. We can have a prediction, a point prediction, and an interval prediction here. So the point value of our prediction here is going to be taken as the single value that we can estimate from our estimated regression line. So we take y hat to be beta hat 0 plus beta hat 1 times x. And this is giving us one single value that we think is going to be correct for the value of an unseen y given x is equal to little x. Okay. We're not expecting this to be exactly correct, but if the model is correct, it should be close to the truth. Now, using that variability of prediction, we can also form a prediction interval. So we can take an interval around that point estimate in order for us to actually estimate our uncertainty here, or to characterize our uncertainty here. The prediction interval is going to be an estimated interval that's going to contain the true unobserved outcome with a set probability. And so it's analogous to a confidence interval, except instead of us trying to get a parameter contained in the interval, we want to get an unobserved data point contained in this interval. Okay. So if we want to take on a 100 times 1 minus alpha prediction interval for the outcome, given x is equal to x, this is going to be equal to y bar plus or minus t times n minus 2 alpha over 2, right? And we want to have the square root of our MSE multiplying this, okay? And so that's going to be the MSE times 1 over n plus this, right? Which we can also just write as this piece down here, okay? And so this is a little bit confusingly put on the slides here. Ultimately, what we're really thinking about here is that we want to take, we can sort of ignore this first component here, okay? And then we're saying that this is going to be y hat plus or minus our critical value times the square root of this component over here, right? Which is the same as what we had in that sort of crossed out region, but was sort of written in a confusing kind of way. All right, so this is going to ultimately give us our prediction interval. This prediction interval is going to look a lot like a confidence interval, right? But the important piece is that we have replaced the standard error over here with the standard error of prediction, right? So we have this 1 plus this other term here. And so that's going to ultimately give us out our prediction interval here. So prediction is going to allow us to use our past data to make educated guesses about what we're going to observe in the future. And that's going to be a very powerful way of using linear regression. So we can take a look at some examples here, right? And with these examples, we're going to be thinking about taking output from statistical software and trying to use that to answer these questions. So we have a biologist studying the relationship between the concentration of a certain plant hormone and the rate of growth in seedlings. They have a study of N equals 63 individuals. They find the following summary statistics and the regression model. Right? And so we're given the mean and standard deviation for both our explanatory factor and our outcome here. We're given our results for our estimated intercept and our estimated slope. We're told that sigma is 3.14, so that's the square root of MSE. We're also given an R-squared value. So we want to predict the expected growth rate with a 99% prediction interval for a seedling with an oxygen concentration of 12. And so to do the prediction, right, we want our point prediction. We simply take 1.4 plus 1.5 times by 12. Right? That's going to be the predicted value out of our model. That's our point estimate here. If we want to then get a 99% confidence interval, well, or a prediction interval rather, with 99% here, we want to figure out, well, what is alpha? Alpha is always going to be 1 minus 99%. Okay, and so we can take alpha to be 0.01, but then we need some other pieces of information. So we're going to need to know the sample size is 63. We're going to need to know that the mean of X is 10.5. We're going to need to know the standard deviation of X in the sample is 5.9. And we're going to need to know that the square root of our MSE is 3.14. And then with all of those, we can plug that into our formula, and that's going to end up giving us a prediction interval. And so we can walk through this and sort of focus on where we're pulling out the information here. So we want to predict the value of y when x is equal to 12. It's going to be given by y hat, which is 1.4 plus 1.5 times by 12, right? 1.4 plus 1.5 times by that value of x is equal to 12. Okay, this gives us a value of 19.4. If we want to form, okay, and so here we have the answer written out for a 95% prediction interval, right? The question had asked for a 99, but we'll walk through with alpha equals 0.05 here, right, instead. So this could be corrected to say a 95% prediction interval here. The mechanics will be the same. We'll just need a different critical value, right? So then we're going to get alpha equals 0.05. We have n is equal to 63, x bar is 10.5, the standard deviation of x is 5.9, and the square root of our MSE is 3.14. Okay, and so then we can sort of pull all of this together. Our critical value is going to ultimately be the Tn minus 2, alpha over 2 critical values. That gives us a 1.9996, right? We get that from taking Qt 0.05 over 2, degrees of freedom is equal to 61, right? So Qt is always going to give us the critical values for our T distribution. 0.05 over 2 is for our alpha equals 0.05, degrees of freedom is 61, right? And so again, while the question asks for a 99% prediction interval, we'll solve this out for a 95% one here. Okay. So to get our prediction interval, we then just turn to our prediction interval formula, and we have to start plugging in our values. So we need our point estimate, that's 19.4. We saw that on the previous slide. We need our critical value, that's 1.9996, right? That's given to us right here. This 3.14 is the square root of our MSE, so that takes care of this first term. And then we have our 1 plus 1 over n is 63. Okay, plus 12 is the value we're predicting for, minus the mean squared, and then we take the total sample size minus 1 times by that variance there, right, which is that 5.9 squared. And that gives us this interval here of 13.07 up to 25.73. Okay, and so ultimately what we're saying is that the predicted growth rate is going to be 19.4 millimeters per day. If our concentration is 12, we have a 95% prediction interval of 13.068 up to 25.732. Okay, and so the process here is going to feel very familiar if you've calculated confidence intervals before, but here we're trying to predict a specific value. And so if we have an observation where we know the concentration is going to be set to 12 in the future, then we're going to predict this value for the specific growth rate as well as to quantify the uncertainty here. So we can take a look at another example here. Again, the example is going to be quite similar, right? So a chemist is going to measure the mass of a chemical product that's produced based on the mass of given reactants. They're running the experiment 37 different settings. We're given some output information here. We want to predict the mass of the chemical produced with a 99% prediction interval if there are 8 grams of the reactant. So once again, right, we want a prediction and we want a prediction interval. Okay, so to get our prediction, we're going to take our intercept, which is 0.73, plus 2.5 times by this 8 value, right? That's the value that we actually want to predict at, and that's going to give us our point prediction here. Okay. And then ultimately, to get our prediction interval, we need to think about what other information do we need. We need to know that the sample size is 37. We need to know that the sample mean of X, so reactant mass is our X value here, is 11.1. Sample standard deviation is 5.2. And the square root of MSE is going to be 0.588, right? So all of that information is going to need to be taken together in order for us to form out our prediction interval here. And so we can take that and we can start to plug in here, right? So we want to predict Y if X is equal to 8. So we take 0.73 plus 2.5 times 8. That gives us 20.73. Okay. For a 99% prediction interval, we're going to want alpha equals 1 minus 0.99, so that's going to be 0.01. This time we're actually doing the 99% interval rather than the 95. Okay, we have n is 37, x bar is 11.1, the standard deviation of x is 5.2, and the square root of our MSE is 0.588. That's all the information that we're going to need to solve this problem here. So we can chug through and get this, right? The critical value we need is going to come from the Tn-2 distribution. That's a T35 distribution in this case. We want 0.05 over 2, right? Alpha is 0.05 here. And so that's going to give us 2.03, negative 2.03. We get this using the Qt function in R, right? Qt, we plug in 0.05 over 2, degrees of freedom is going to be 35. That will give us our T critical value. That's going to spit out that 2.03. For the prediction interval, we then take 20.73 plus or minus the critical value times the square root of the MSE times by, and then we have that form in brackets there, right? So the 1 plus 1 over n plus x minus its mean squared over the n minus 1 times b by the sample variance. And so if we work through that whole calculation, plugging all of the values in, we get 19.515 to 21.946. Okay, and so what we're saying here is that we're going to predict that there is going to be a product mass of 20.73 grams if the reactants have a mass of 8 grams, and we have our 99% prediction interval between 19.52 and 21.95. Right? And so this is going to be, again, an observation that we have not yet made. If we're making an observation in the future where we give the reactants 8 grams of mass, then we're predicting that there's going to be products of 20.73 grams of mass. Okay, and so ultimately, we are thinking about observing something in the future, and we're trying to predict what that value is going to be based on our observations of the past. We can look at our third example here. So we have a rehab clinic who wants to determine the relationship between the weekly time that a patient spends in physical therapy and their improvement in a standardized mobility score. So they collect data on 100 patients and obtain the following. So again, we have very similar output here. We want to predict the mobility score improvement with a 90% prediction interval for a patient who spends 10 hours in therapy per week. Right? So again, we want to predict when x is equal to 10. So we take our intercept plus our slope times by 10, that gives us a prediction. We want to have a 90% prediction interval, so here alpha is going to be 10%, right? We need to know that n is going to be 100, that's going to give us a T98 distribution, right? We're going to need x bar to be 5.49, we need the standard deviation of x to be 2.56, and we need the square root of MSE to be 2.91. All of that's going to get plugged into the formula that we have for our prediction interval, and then we can calculate out the specific interval here. Okay, so we want to predict y if x is equal to 10. We get 5 plus 2 times 10 gives us 25 as the point estimate. For a 90% prediction interval, we have alpha is going to be 1 minus 0.9, gives us 10% on alpha. So we're observing n is equal to 10, x bar is equal to 5.49, standard deviation of x is 2.56, and the square root of MSE is 2.91. Ultimately, we want to form out our prediction interval here. So we need to get our critical value. That's going to be from the Tn-2 or the T98 distribution in this case, right? We want alpha over 2, which is going to be 0.1 divided by 2. So this is going to give us 1.6606. We can get this in R using the Qt function. The Qt function is going to take 0.1 over 2 as the level, and then the degrees of freedom is going to be 98. Taking all of this, we plug it into our prediction interval formula here. We get our estimated value plus or minus our critical value times by the square root of MSE, which is 2.91, and then everything plugged in to the standard error part of the formula there. All right, so that ultimately gives us 2.07 to 29.93. And so then again, what we're saying is that if we know that a patient is going to spend 10 hours per week on therapy, we're going to predict that they will have a mobility score of 25 with their 90% prediction interval between 20, say around 20 up to around 30, right? So it's going to be in that interval there. So again, this is a patient that we have not seen in our data before. We're predicting the value out of sample. Our final example here, we want to explore the relationship between an individual's levels of extroversion and their score on a standardized anxiety assessment. We have a sample of n equals 50 and they observe the following results. So we want to predict the anxiety score with a 99% prediction interval for an individual who scores 5 on extroversion. And so again, we go through and we say, well, we want to predict y given that x is equal to 5. So we take 34 minus 3.7 times by 5, right? That's going to give us our point estimate here. If we then want our prediction interval, well, we want 99%, so alpha is going to be 0.01. We have n is equal to 50. We have our mean of x is 3.09. We have our variance of x is going to be 1.17 squared. The MSE, square root of MSE is 2.82. And so then all of this can come together to form out our prediction interval here. All right, so plugging in to get y when x is equal to 5, 34 minus 3.7 times 5 gives us an estimated value of 15.5, or a predicted value of 15.5. 99% prediction interval, we have alpha is equal to 0.01. Right, we're observing n is equal to 50, x bar is 3.09, the standard deviation of x is 1.17, and the square root of MSE is 2.82. Right, that's all of the information that we need to extract here. So we get our critical value. Critical value is coming from the Tn-2, so the T48 distribution, we need to 0.01 divided by 2. That's going to give us 2.6822. Right, this is going to be coming from a critical value Qt 0.01 over 2 with degrees of freedom is equal to 48. Okay, if we want our prediction interval, we plug into our formula here. So we get our 15.5 plus or minus our critical value times by the square root of our MSE, right? And then the standard error part of the formula there. Ultimately, working through the calculation here gives us a 7.66 up to a 23.34. Right, and so again, we're told that if we were to know someone was coming in with an extroversion score of 5, we would predict that they'll score 15.5 on the social anxiety test assessment that we have here. We have our 99% prediction interval to say that that should be between 7.66 and 23.34. Right, and so again, this is for an individual that we have not seen in our data before. We're thinking about predicting out into the future. Okay, so because we're dealing with interval estimation here, or we're forming these intervals, there is quite a lot of similarity between prediction intervals and confidence intervals. And so it's worth exploring the relationship here between confidence intervals and prediction intervals. Specifically, the other way that we can view what we're doing with our regression is to view it as an estimation of the conditional mean. So we're trying to estimate the value of the expected value of y given x is equal to x. If we then form a confidence interval for this, we get that the confidence interval is going to be y hat plus or minus our critical value times by the square root of our MSE times 1 over n plus x minus x bar squared over n minus 1 times by the variance here. Okay, and so this looks a lot like the intervals we were just using, right? There's a very subtle difference, and so it's sort of important for us to think about, well, what's happening with our confidence interval, and why does that differ from what's happening with our prediction interval, right? And there's going to be both a conceptual and a practical distinction between these two different approaches. Conceptually, if we're estimating the conditional mean, this is an estimation problem, which is us trying to infer the value of an unknown parameter, right? In this case, it's going to be the value of an unknown parameter in the conditional distribution of y given x is equal to some value, right? There is some distribution out there for the outcome given the value of the explanatory variable. And what we're trying to say is, well, what is the mean of that distribution? And it's going to turn out that we can be a little bit more certain about what the mean of that distribution is compared to our prediction problem, which is saying, if we have one specific individual who takes on a specific value, what is the value that they're going to have for their outcome, right? So it's going to be, in our estimation problem, we're thinking about reflecting the conditional distribution of the observations that have already been observed, right? We have already made a bunch of draws from that conditional distribution. And we want to sort of reflect that distribution back. We want to infer values about that distribution. Conversely, with prediction, we're trying to infer the value of something that has not yet been seen. We want to say, one specific person, what is your value going to be in the future? Okay, and this is going to be sort of a more difficult problem for us to say. Now, practically, what we are saying here is that there's going to be less certainty when we're doing prediction than when we're doing estimation, right? And the way that we can see this is because we have in our prediction interval, we have this 1 plus term, right? So if we think about, well, what is the actual difference in the formula here, right? The first component of this formula, this y bar plus or minus this critical value, that's exactly the same. We have the square root of MSE, that's still exactly the same. We also have this 1 over n plus x minus x bar squared, and so forth, right? So the only difference is that in the case of our prediction, we add a 1 into here, right? So this is going to be all of this, except we have a plus 1 in here, right? So plus 1 inside of that brackets. And so what we're saying is that we're increasing our variability ever so slightly. We're increasing our variability with this extra 1 here. And so we're going to take essentially the same interval, except we're saying we're a little bit less certain about this. So we get our plus 1 here, and that's going to be the new interval that we have. Okay, and so ultimately, the problem of predicting the conditional mean, or of estimating the conditional mean, or predicting a value in the future, is going to be deeply related problems. We're going to get the same point values for both of them. We get the same point estimate as our point prediction, right? But the uncertainty that we have around them is going to differ. With the estimation, we can be a little bit more certain, and that's because we're reflecting an entire distribution, something that we have many observations for. Whereas with prediction, we're trying to guess the single value into the future, right? And so we have that epsilon uncertainty that's left over there. Okay, this extra error is coming because we have inherent uncertainty in the random error from that epsilon term. Okay, so because epsilon has sigma error, then we're going to have that extra error reflected in prediction. Now, it's also important for us to think about, well, what are the limitations of prediction, right? Because prediction is a very powerful tool. We're going to be able to make guesses as to the values of unseen data, right? And that's going to be very useful for us, but it is going to be limited in certain ways. And so we should sort of make sure that we're aware of those limitations. So the first piece is that we have to be careful not to extrapolate when we're predicting observations. And so what are we meaning exactly by this? Well, prediction is going to rely on the model that we already have to accurately fit future data, right? So the idea is that we've seen a bunch of data in the past, we fit a model based on that data, and then we're using that model to predict information in the future. So as long as the data in the future looks like our data from our past, then that's going to be okay. So it's relying on what we've actually seen in order to make predictions about the future. So if future data look like observed data, that's going to be totally fine. However, extrapolation is going to occur if you predict beyond the limits of your observed data. So if you only, say, observe your explanatory factors between a range, maybe you only observe x values between 0 and 10, right? If in the future you observe x is equal to 50, right, that's way beyond the range of your observed data. And so it's not easy for you to say the same model is going to hold all across that range, right? And so we have to be careful about that, because in our data, we never saw anything with x equals 50. We didn't see anything that was close to x equals 50. And so if we want to predict x equals 50, we have to be very confident that it's going to be the same pattern all across the data, but we can't actually infer that from the data itself. Right, so if we have values for our explanatory factor that are above or below those values observed in the sample, then what we're doing is extrapolation. And extrapolation is not generally supported by the theory of linear regression. If you want to do extrapolation, you need to be supporting this scientifically. You need to be able to say, well, the exact scientific pattern, the exact scientific relationship should hold over this whole range, not over the limited range that we're looking at. Okay. Prediction is going to be making the implicit assumption that there is no systematic changes in the underlying model, right, between the past and the future. If something changes at some point, right, that changes how the outcome is expected to react to the inputs, right, then that's going to be reflected in needing a new model in this prediction, right? So we need to sort of recognize that in order for us to predict the future, we're making the explicit assumption, sometimes it's left implicit, but we should try to make it explicit, that the past and the future are going to look alike. And they don't have to be exactly alike, but that they're going to look enough alike that we can learn about the future from the past. Okay. There's not going to typically be means of testing predictions as they arise, meaning that we have to be trusting our observed information. As you perform your predictions, if you're making decisions based on these predictions, right, it's not until after the actual result has happened that you'll know if your prediction was correct or not. If your prediction was not correct, there may have already been consequences for this, right? And so we need to really be able to trust that the future is going to look like the past. So we can frame the simple linear regression as a predictive model, right? And if we do this, then we can get point predictions using our point estimated values from our linear regression model. And we can also get prediction intervals, which look a lot like confidence intervals, but instead are quantifying the uncertainty of our prediction rather than the uncertainty of our estimation. There's going to be more uncertainty in prediction than there is in estimation. And when we're doing prediction, we need to be very cautious that we're not predicting beyond the limits of our model. So we're not trying to extrapolate beyond the values, whether that is literally extrapolating beyond the range of values that we've seen before, or extrapolating beyond the capacity of our model. So we're not taking into account the effects of systemic changes, for instance. If we think that the model is a good fit, if the past is going to look like the future, then linear regression is going to become a very powerful tool for us to be able to infer the values of observations that we've not yet seen based on those that we actually have seen. And more than that, we can quantify how certain we can be in those guesses of those unseen values.